Oh, I must have gotten something. These I've been sniffling all day.
Yeah, well, 'tis the season. Okay, I want to clear up some confusion with these rotations. Remember we had J1. Let's see, they're all anti-symmetric. Minus 1. I just forgot the way I used
Zero,
it.
0, minus 1.
What's that?
0, 0, minus 1 in the row. In the top row, 0, 0, minus 1.
Oh, yeah.
And then the bottom. And then everything else is, yeah.
Yeah. There's a way to remember them.
Oh.
And that's what I forgot. That's, you know, I woke up this morning and thought, duh, because the mnemonic for these makes them very easy to work with.
Mm-hmm.
All right, so JI is, let me just be sure. If we look at the JK components of that, it's just the Levi-Chibouda tensor.
Mm-hmm.
All right, so for J1, all right, so JK, this is going to be epsilon 1 JK. Well, J and K have to be 2 and 3 or 3 and 2. So if it's 1, 2, 3, then the 2, 3 component, so row 2, column 3 is 1.
Mm-hmm.
And then when it's KJ, this is minus 1.
Mm-hmm.
So that's row 3, column 2 is minus 1.
Yeah.
Right? So it fills out these matrices like that. But then if we have to multiply these things together and take powers, we're just taking powers of the Levi-Chibouda tensor. And we can write those in terms of Kroneckers, and it's all much easier. So I'm just going to do that again and count on Mubarak to edit out the end of the last lecture. It's where I got, I mean, we forced our way through it, and it wasn't too bad, but it is actually a lot easier to see this way and will lead us directly to the geometric interpretation of the result. Okay, so now we do the infinitesimal expansion and write a finite transformation. Let me call this phi. What would I do with my notes here? I think I called it phi. Yeah. As the limit as n goes to infinity, holding n epsilon constant of the identity plus, and now I'm going to write a general linear combination of these can be written as a 3-vector dot J. So any anti-symmetric matrix, 3x3 matrix, can be written this way. Then I'm going to write W as, for the infinitesimal case, it'll just be epsilon times some unit vector, or in general, we'll end up with phi times some unit vector. But these will be the infinitesimal ones here. So we just have some linear combination of the J's times epsilon, then that infinitesimal transformation raised to the nth power, and we take a limit. Now, we showed last time that the combinatorics of this using the binomial expansion will make this into an exponential. And it'll be an exponential in this n epsilon, so we have phi n dot j. Or we could write that as e to the w dot j. Excuse me. It turns out that this notation is better where we separate the magnitude and direction of the vector w. So, that's going to be too distracting. Just make sure the door's unlocked. Thanks. Davis, you missed the thing that makes all of this much simpler. The J's that I introduced last time, they're just the Levi-Civita tensor, right? So the ith one of these, 1, 2, 3, has jk components, epsilon I jk. So now when we take powers, we're just taking powers of the Levi-Civita tensor, and that's comparatively easy. So let's do that. Let's just start looking at powers. So n dot j, let's look at the mn component. That's just n dot j. That's going to be ni epsilon I m n. Now here we're in Euclidean 3 space, so the position of the indices on the epsilon don't really matter. We're raising and lowering with the
Kronecker delta.
Well, with the Kronecker metric, basically.
Yeah.
The identity as the metric.
Yeah.
Okay, so nothing more to say there. If I square this, so we look at the components of this squared, it's going to be 2 of these. Ni epsilon I m k, shall we say, multiplied by nj with epsilon j k n. And now we pull out the ni and nj, so we're not dealing with all those ABC components anymore. And we have a product of 2 epsilons. Now, this has the k at the end, this has the k in the middle, so I'm going to interchange one pair here to write epsilon I m k, epsilon j n k, summed on k. And I think you've all seen this identity enough to know, all right, since these 2 indices are the same, either I equals j and m equals n, or I equals n and m equals j. So we get 2 terms here, and the normalization, well, is correct. Delta ij, that's the metric. What? Let me see how what I called that. Yeah. So when I write both indices down, that's the Euclidean metric. Okay. And then this is the Kronecker delta mn. As you know, they're the same numerical things, but slightly different. And then we need delta I n and Kronecker m j, like that. And now this is easy to evaluate. Ni and j on a metric, n is a unit vector, so that's just 1. So we get minus a Kronecker m n, an identity matrix. And then here we have plus, and then this changes the nj becomes nm, and then the ni is lowered to an n sub n. This object is a projection operator, right? What defines a projection operator? What property do we check?
Squaring to itself or something?
Squares to itself, yeah, idempotent. So we check delta m n minus n m n n with delta nk minus n n n k equals, okay, here we get a Kronecker mk. Here we get minus n m n k. Here we get minus n m n k. And here we get plus, okay, n down with n up, what's that?
That's the identity.
No.
That's what you call the identity. It's the the square.
It's a sum.
The square, yeah.
It's n dot n, where n is a unit vector.
I
It's like a
understand
product.
Yeah, we're summing here. So,
Yeah.
so it's n squared, but it's a unit vector, so it's the number 1.
Yeah.
Not the identity matrix, it's just the number 1. Then we're left with a matrix n, m, n, k. So two of these cancel, and we're left with this operator.
Cool.
And it's actually easy to see what projection it does, right? Just let it act. What's it orthogonal to? Can you see it? Let it act on an n. Right? Kroneker's going to give us an m, but then n dot n is 1
So just minus
times n m is 0.
0.
So it's a projection operator orthogonal to n, orthogonal to that unit vector. Does that make sense?
Mm-hmm.
So you're subtracting off, if this were, say, in the z direction, then that outer product is just zeros everywhere except down here. And then this is the identity, 1, 1, 1. So the projection is into the xy plane. You see?
The z plane vanishes.
The what does?
The z plane vanishes.
Yes, exactly.
So,
Yeah, in general, it's the plane defined by this n. So we're subtracting off a matrix built in the n direction from the identity. That's always going to just leave us with everything orthogonal to n. And look at it. Let M be any matrix that's orthogonal to n. You can prove that claim by just testing it on any vector orthogonal. Well, if they're orthogonal, that dot product is 0, and you just end up with M again. Sorry to use the same symbols and indices, but you see what's happening. Okay?
mm-hmm.
All right, so that happens to be a projection operator. That doesn't help us take powers of it, but, well, actually it does. Knowing that this annihilates n might make the next thing simpler. Let's look at any rate at n dot j cubed. N component, right, that's going to be the square, which is minus this projection, delta n, that's the m k minus n m n k, times one more n epsilon I, and then we need k n here to end up with free mn indices matching here. Just shout if you have any question on what we're doing. Okay, so this first term, and I, the k becomes an m, and we have epsilon I m n. Then the last term plus we have an m and k and I epsilon, and what is this? Not so clear, let me rewrite it. Let's put all these indices up. Does that help?
Oh, just nm, because ik is flipped for n. Okay.
What's that do? The fact that we've got two n's here. This is actually a triple product. Right? When you put three vectors on an epsilon, that's, A dot B cross C.
Yeah, but we have the I and k flipped on the other side of the n and n.
I guess that would.
I can interchange those. Those
Okay.
are just numbers.
Okay.
That doesn't matter. But notice you have the same vector twice. Okay, let's try this. The cross product of A and B, the I component can be written as epsilon I j k A j b k. Right? That does the anti-symmetrization, gives you each component.
Yes,
So
we know this.
look at that. Look at that. What is that?
Oh, so it just gives us the j component or the n component according to that.
It's the n component of what?
Of A cross.
N cross n cross n.
Well, yeah, sure. In that notation,
Well, it's
N
a triple
cross
product. This is
Okay.
n dot n cross
Cross.
n.
Okay.
Right?
Okay.
And
Come on, guys. You know this. You know this.
yeah.
What happens when you contract a symmetric thing with an anti-symmetric thing?
Goes to 0.
Yeah, so don't say it with a question mark on the end.
It goes to zero.
Absolute certainty.
If you have a statement like that with a question mark on the end, go try to prove it. And the next time you say it, you make it a claim.
Don't worry, we take off the question mark.
This is identical. So that term's gone.
We would rather take off the question mark than go try to prove it.
Oh man. That's pretty funny.
The M component. So we're back to where we started, except with the minus sign. Let's see. That was? Is this the right power squared cube? Cube that comes back with a minus sign. Yeah, okay, so the fourth power, is this right? The fourth power is going to be minus this squared, which is our symmetric tensor again. But now, right, notice where was it back here? You know, this is minus our projection operator. So n.j squared is minus this projection operator. So here we have minus the projection operator, and then we're bringing in one more n.j, so we're going to get another minus sign, and it'll be back to plus. So we're right back where we started after 4 of these. No, we're not. I'm sorry. This is the projection. It's plus the projection operator. Delta m n minus n m n n. Even powers give the projection operator. Odd powers give plus or minus the original matrix. So now we can write all of the matrices. We can write n.j to the 2k, any even power. The components of that, mn, are going to be what? Well, it alternates in sign. So if k is 0, well, that's 1. If k is 2, if k is 1, we get plus. Signs are just backwards. Let's see.
How do we know that that thing becomes that dot product there? 2 indices are different back when you were doing that a moment ago. So we have an n to nm, and then we have an epsilon with an n.
Sorry, where are you?
Hand a little bit lower, right there, that line.
Mm-hmm.
Yeah, because there's an nm and then an epsilon ij n.
Oh,
Yeah.
oh, sorry, it's not the dot product, it's the outer product. If those were contracted, it would be the triple product.
Yeah.
This is actually just the nth component of the
Oh,
cross
okay.
product.
Okay.
Yeah, sorry about that. But still, you still have n cross n.
Sure. Yeah.
Right?
Yep.
It's 0.
Mm-hmm.
But yeah, that's not contracted yet.
Yeah.
Good. Okay, so then this gives us the projection mn minus n m and n. Okay, so even powers are going to give us plus or minus the projection operator. Odd powers give us our original element of the Lie algebra back. 2k plus 1, the mn component, will be, again, we get minus 1 to the k. So when k is 1 here, that's cubed. That's this one where we have a minus sign. So that works right. And then we have n dot j, the mn component. So now we've found every power of the matrix. And we just write out the exponential. Split the exponential into 2 parts. And this time, we're going to find it much easier to put the to write it back into vector notation. Okay. Did we do this last summer? Have we done this?
Yeah.
Yeah, you've seen this,
Yeah,
right?
yeah.
Okay, yeah.
So, yeah.
So I should get you up here to do it. Yeah.
No more yeah.
What are you laughing at?
In that case, he's gonna drop the class.
So, an orthogonal transformation. Let me call this R. We know it's given by the exponential of phi n dot j.
Mm-hmm.
So tell me what to do. Utter silence.
Yeah, what I'm trying to get.
Well, we know it equals itself.
Right, and so we need another way of writing itself.
Yes.
Yeah.
So we have all the n.j's now.
Yeah, we've got the power series, right?
Yeah. So we can start writing those out.
So let's write the power series.
Yeah.
Of course, this is, we'll say m.
Oh, just like we
0
did
to
before in the
infinity.
previous one.
Oh, yeah. So we have 1 over m factorial phi n dot j to the m. Okay, there's the exponential. But now what do I want to do with that series?
Break it into odd and even.
Exactly. Yeah. Exactly. So we write all the, let's write all the odd terms. So we'll write k equals 0 to infinity. But now we want odd pieces here, 2k plus 1 factorial. We have phi is just a scalar to the 2k plus 1. So when k is 0, we start with 1, then 3, and okay, so we're getting all the powers here. And then we have n dot j to the 2k plus 1. And we know how to substitute for that. Now we need the even ones. All right, and here we have to be a little bit careful.
You can't start from 0.
We can't start from 0 because j dot n dot j to the 0 power is 1. So we have a 1 here. And then we have the sum k equals 1 to infinity of 1 over 2k factorial. So when k gets to be 1, now we have these terms over here.
Yeah.
And I forgot my minus 1. Oh, we're going to get the minus 1 to the k, right? Phi to the 2k, n dot j to the 2k. So now we've written the exponential in terms of the odd and even powers, and we know what those are. So now we just substitute. And here's where we get a minus 1 to the k, phi to the 2k plus 1 over 2k plus 1 factorial. And that, we know what that is. And then the odd powers here are going to give us the just a single n dot j, which comes out of the sum because it no longer depends on k. We've gotten the matrix out of the sum, and this is just some function. Then we have the identity. And now,
Plus.
yeah, what we really need here, right? This is going to be that projection operator.
Yeah.
Right? So what we need to do is we're going to need, let's see, we're going to need the 0th power times that projection operator. So if we subtract the projection operator, 1 minus, it's basically an outer product of n with itself. Let's just use this dyadic notation.
Yeah.
We know what that is. If you put AB components, Kronecker, and NA and B. So we've subtracted that. Now we can add it back in because we get it here. So now we'll have the sum k equals 0 to infinity minus 1 to the k, phi to the 2k over 2k factorial. And then coming out of the whole thing, we'll have the identity minus n.
So that's an equal sign, you said?
What's that?
That's an equal sign?
No. Plus.
Okay.
Yeah, it equals our rotation.
Yeah, that's right.
Okay, so what are the functions?
Sign.
Yeah, which is which?
Oh, that's a sign. Yeah.
Last
Last time we talked about this.
Cosine. Cosine is even, sine is odd.
Except I was
And-
too stupid back
Okay, so
Smart enough to learn that.
so let's see what we've got.
Now it's like, okay,
We have n
okay, we can.
dyadic notation. These ones cancel, and then we have 1 minus n times cos phi, and we have n dot j sine phi. So this should be our rotation matrix, and let's see if we can understand what that object is. Easiest way to do that, assuming we got it right here, is to let it act on a vector. So here's the picture. Suppose we have our unit vector n going off in some direction, and let's let v be an arbitrary other vector. Then what we want to do is act with r on v. So this is going to give us some new vector. What is it? So I'm going to let all of this act on n, but what's easiest is if I mn the n, do it in components. So what have we got? We've got nm and n plus 1 minus that.
How come we have that extra little NN and not the one, not the identity matrix there? Maybe.
We had two identities.
Yeah, but
Those cancel.
that
And we're
one,
left with the part of the projection.
and then.
Right, we
Oh,
subtracted and
okay.
added the
Oh.
0th term here.
Okay, I see. Yeah, I was factoring and then doing something else.
Not quite that fancy.
Yeah.
Yeah, so then this is just sitting out here and we can subtract the identity.
Hmm.
So, right, here we have delta m n minus n m n n cos phi, sorry. I think we're done with these powers. Now, I've got a homework problem for you guys. I want you to do all of this with SU2. Right, so go through the same procedure, and I want you to show that using SU2 on a vector, you get that same rotation matrix. Right? Good exercise. It'll take you, it'll take you a little while, but that's a good one. Okay, then here,
Do it in lakes.
yeah, you can do it in links. That's all right. We have ni epsilon I m n for this term. That's times sine phi. And we're going to let that act on Vn. So I'm going to start mixing notation a little. We have nm, and then this is n dot v. Then here we have Vm. Let's see, I'm going to write this as a vector.
Sure.
This just gives V, and this gives minus n hat n dot V. Goes fine. And And then this one, let's watch our signs here. Interchange M and N. And now we have the cross product, N cross V. So we're going to get minus N cross V. Well, let's see, this would be the M component of that, and then times sine phi. Okay, now, what is this? It helps to define V parallel is a vector along n. So you take the component of V in the n direction, multiply by n, and that's the part of V. So yeah, I'm taking the dot product here. I'm going to write V as this is going to be V parallel, and then that one is going to be V perpendicular.
Yep.
Then there's another vector, N cross V perpendicular, that points out of the board.
Right.
Yeah, so we'll have a nice orthogonal basis. Now, what do we need? V, this one, V perpendicular, is what, right? That's exactly this. It's V minus the part along N. This is just now V parallel. So V minus V parallel is V perpendicular. Good? Mm-hmm. And then N cross V, okay, N cross V is a vector out of the board. And let's see, its magnitude, let's look at N cross V. Let's see, what is this? It's out of the board. And its magnitude, what's its magnitude? It's magnitude of N, magnitude of V, times the sine of theta. So its magnitude is V perpendicular. So let's let V perpendicular be defined as the magnitude of the vector V perpendicular. Then I can write this as this is V parallel. So R acting on V vector is going to be V parallel. Then plus two terms, we have V perpendicular times cosine phi. And then we have minus, what should we call this? Well, let's just leave it N cross V. N hat cross, let's see, how can we write this? Let's see, let's let M be defined as a unit vector perpendicular to N, perpendicular to V. Okay, so that's a unit vector out of the board. So N cross V is just V perpendicular times M hat. This is, oh yeah, there we go. Let's use unit vectors everywhere. Let's let this perpendicular part equal the magnitude times some K hat. So we have unit vectors, we have a K hat this way, and coming out of the board is M hat in the N cross K hat direction. So now this is in the K hat direction, and we have V perp magnitude. Here we have V perp magnitude in the M hat direction, sine phi. And now it's really clear what this is. The part of V parallel to N does not change. We're doing a rotation around N, right? So the part of V along N doesn't change. Then in the plane perpendicular. So now we look at just this V perpendicular, and that's a simple rotation, cosine and sine. For the like the component in the plane and the component out of the plane of a vector of length V perpendicular, the new vector is rotated by phi around n. So geometrically, it becomes completely clear what this rotation is doing. And the parameters we're using to specify it, believe me, this is a lot better than the Euler angles. Right? If you've ever used those, or if you haven't used those, look in Goldstein.
Yep.
Right? It's a horrible, horrible matrix. This is a lot cleaner. There's a direct interpretation of the rotation in terms of the parameters. So, your homework, I won't even call it an exercise. All those other ones in the chapter are just exercises. So, show that SU2 rotates V exactly the same way. And now I've got to show you a bit of stuff preparatory.
Use the restroom.
Okay. So let me tell you a bit of stuff about SU2. It's possible that's the next topic anyway. We haven't talked about the algebras in general yet, have we?
I think elsewhere we have. Elsewhere we have.
Elsewhere we have, right?
It kind of went into what we're doing here, didn't it?
Okay, yeah, what I do in the rest of this, I'm going to jump ahead a little bit. I've labeled one of the sections here as optional.
Which section is that?
Well, it's called From Lie Groups to Lie Algebra, section 1.2.
Yeah.
What I do in that section is to show that, all right, if you have a group and you have the Lie algebra you get from that group, I show almost completely, not quite, that the properties that define the group require exactly the properties that we demand of a Lie algebra, that it be a vector space with an anti-symmetric product and the Jacobi identity. The Jacobi identity comes from associativity of the group. The closure is actually what leads to the commutation relations. And then let's see, the identity is easy. There's just the identity.
The inverse.
What's that?
Multiplicative inverse in a group.
Yeah, the inverse. Yeah, okay. When you use the inverse property and the closure, what you do is you construct an object G1, G2, G1 inverse, G2 inverse, and you expand that to probably you need cubic order or something, and it boils down to the commutation relation. Right? This has to close into some G3. So you expand everything infinitesimally, and you can get the commutation relation, and the fact that it needs to be structure constants that define it.
We've done that before.
Yeah, we've worked through all that. So that's written out in this section. Then there was one more. What was that just before this? Oh, now we probably do need this, except I know I've worked through it with you two. The commutation relations, there are a couple of exercises here, but then I go on to find the generators in n dimensions.
Mm-hmm.
All right, and we can write those. There's still these anti-symmetric things. What you need is a way to write a general anti-symmetric matrix, but you can't do it any longer with the Levi-Civita tensor.
Mm-hmm.
But it's easy to write a bunch of antisymmetric matrices if you choose the labeling for your matrices right. So our generators for the infinitesimal generators for the arbitrary for an arbitrary SOPQ. I'm going to label them with a pair of indices. Okay, so these are antisymmetric, and I sum with my generators like this, and these linear combinations need to be an antisymmetric matrix. Let me write that with, Mn. So I can write my generators. Usually we're going to want a half here because I'm double counting. What we do is, instead of putting a single index on the generators like Ji, right, I'm going to put a pair of indices that tell which plane is getting rotated. So the 1,3 plane or the 2,7 plane, that's what goes here. And I define it so that this is antisymmetric, so when I contract with antisymmetric arbitrary coefficients here, I just double count. So I divide by 2. Then this thing, MRS, is going to have components MN. And now these are antisymmetric and those are antisymmetric, so I can do it with Kroneckers. RM delta SN minus delta RN delta SM. And then the generators, we need to be able to multiply generators. They need to be 1-1 tensors. So I raise this using the metric. Well, let's suppose our metric here is eta Mn. So a bunch of ones, P1s and Q minus ones.
Yep.
And then the range of these is the same as the range of those. Raising an index on this side, RS Mn, is going to raise M over here and turn it into the metric. So I'll have Rm delta Sn minus delta, and then I'm going to raise the M here, Sm delta Rn, like that. I can write those in either order, they're just numbers. So this forms a complete basis for antisymmetric matrices in however many dimensions we're in, n dimensions, p plus q dimensions. And now we can multiply these, we can find the commutation relations of these. And I think we've done that, so I might not repeat it here, but let's say RS, well, what are some letters? Let's just use AB.
Sure.
Okay, and this is going to have some components, M, N. So, in fact, you have to have enough indices that you can multiply a pair of these and then anti-symmetrize it. So here we're going to have, let's see, eta, RS. Let's see. All right, hey, let me do this differently. Let me take the indices from the beginning of the alphabet, like AB, and MNRS from the middle. Excuse me. These are just labels telling us which generator we've got. So now we can take. So we need this is going to be A delta S B, but I'm going to sum on it, so I'll put C minus raising an index gives eta S A Kronecker R C. Then I'm going to multiply that by an MN one, so eta M C delta N B minus eta n c delta m b.
Why do you write C instead of B again?
I'm summing C here with there, so I'm multiplying two matrices of this general form.
Okay.
All right. So the down index here is contracted with the up one there. So yeah, so basically what I've written is MRS. I've got the AC component with MN with the CB component. So this is what I've written here.
Okay.
And then I'm going to subtract the other one. Now, let me ask. You guys have seen this. Should I go through this? You want to see?
Yeah, I think it's good. I think it's useful.
Right. Okay. So we're going to subtract. Well, we have to interchange which generators we're talking about.
But
The index structure will be the same.
flip it over.
Yeah. So the RS will become MN and vice versa.
Mm-hmm.
So eta. Let's see. RS becomes MN. MA delta NC minus eta
And
N A delta MC. And this becomes R. Let's make an R intelligible. C delta S. R S B minus eta S C delta R B.
Yeah.
Okay, so we just multiply all that out. And then we recollect things. This isn't so bad, it's just that there are a lot of terms to keep track of. But remember, we're finding the Lie algebra of the rotation group SOPQ, where P and Q are arbitrary, P plus Q equal n dimensions. So this is good in any dimension. We're doing a whole lot when we do this. So continuing here. All right, it's only the C that's summed. So we still have eta RA. Then the Kronecker hidden system gives eta MS. And then we have Kronecker SC. Then the first one there with the last one, we have minus eta RA. Then the Kronecker SC makes this NC. And, C gives S. And then finally delta MB. Then the second one here with the first one, eta SA. The Kronecker makes it eta MR. And then we have a delta RC. Delta NB, excuse me. And finally a plus. And eta SA. Then eta NR. And finally delta MB.
Should there be two upper S indices in that first eta term, RA, eta MS?
No, of course not. What probably should be an N. Let's see. Yeah, it should be. No, that's just wrong. Let's see what that is. That's the very first one. It should have been an NB.
yeah.
Okay. Now, subtract the interchange. Let's see if we can just do this. So, eta. We interchange M and R and N and S, right? So we're going to have M, A, eta, R, S. But we're also interchanging S and N, so this becomes N delta S B. Is this going to work? You guys good with this?
Yeah.
I'm just doing two pair interchanges here. So now we have plus eta M, A. Eta, N goes to S, S goes to N, delta M goes to R, minus eta S goes to N, M goes to R goes to M, N goes to S, B, minus, that's plus, eta S goes to N, A, eta N goes to S, R goes to M goes to R, B. 8 terms. Now, in order for this Lie algebra to close, this has to close back into the M's. So we need to make this look like a sum of constants times M's. And there's a key to doing it because the final expression needs to be matrices, and the free indices, if we look way back here, are AB.
Yeah.
So in each term, there's something with an A and something with a B. That has to be part of an M, right? The rest is just structure constant. So what I do, okay, the one with A and the one with B are part of a matrix in each term. The other one, all right, notice the other one only has labels, not indices. That's because it's part of the structure constant. So what I do is I collect things with the same labels. MS, well, there ought to be something with, there we go, MS.
Yeah.
So
Definitely.
we're going to have one term with an eta MS. Eta is symmetric. But then here, eta RA delta NB minus eta NA
delta R.
N delta RB. Good,
Yeah.
thank you. Okay, next one. Here's minus eta NS. That's the one with the labels.
Yeah.
So we're going to get eta RA delta MB. And
The plus
where's the next one? Here it is.
eta MA.
So opposite sign, there's a
Minus.
minus here, and it just interchanges. MA delta RB. I mean, you know, from the math, this has to work. It's got to come back into M's. All right, we know these are generators for Lie algebra, so the commutators have to close.
2 more.
Okay, so
Eta
let's look at MR here, and that would be this one.
That one.
So we have minus eta MR, eta SA delta NB, minus eta
NA.
NA delta SB, it better be. Is that right?
Yes.
Good. And finally, I'm
Eta
betting on a plus.
The NR.
So we've got all of this and
And
all
R.
of that. So eta NR, eta SA delta MB minus eta
MA.
MA delta
SB.
SB. All right. And that,
And then we can use our definition of those M's over there to rewrite it in terms of M, big M's.
exactly.
Yeah.
This is M. This is going to be Rn. It's going to be the A component every time. So I'm going to put AB out here
Yeah.
and just write the names of the matrices inside.
And then you,
So then we get eta NS MRM minus eta MR MSN plus eta NR MSM. And now, looking from first to last, we have a matrix commutator equals a matrix commutator equal in every component. That means the matrices themselves are equal. And so we can write that the commutator of the matrix with label RS with the matrix with label MN is equal to the term in brackets here. Eta MS MRN minus eta NS. We drop the indices. RM minus eta MR MSN plus eta NR MSN. And that is the Lie algebra of SOPQ. Right, now, we're going to see this again. which is why I took the time to go through it, besides your urging. I'm glad we did do that.
Yeah.
Where we're going to see it is in the spin representation.
Mm-hmm.
So what we're going to be able to do here is come up with a complex representation for some group. We'll call it spin PQ. And we will show that we're able to construct a set of complex matrices that satisfy exactly this relationship, thereby proving that it also is a representation of SOPQ. It's a big one. In n dimensions, the matrices are 2 to the n over 2 by 2 to the n over 2. So that's not so big. If n is 4, then n over 2 is 2. So, they're 2 to the 2 is 4 by 4. The gamma matrices, the Dirac gamma matrices are 4 by 4. And we're able to write some generators, 4 by 4 generators, that are in fact satisfy these relationships. Mm-hmm. But if we go to, let's say, 10 dimensions, all right, you're doing string theory, right? Mm-hmm. So 2 to the 10 over is 2 to the 5th, that's 32 by 32 matrices. So it's a 32-dimensional complex vector representation. Mm-hmm. What that means is, all right, these are called spin or Spinor representations. The vector space on which these generators act, the complex ones, is the space of spinors for that group. So in 10 dimensions, the spinors have 32 components. Big things, right? What happens as you break the symmetry, those 32 break into 8 4-component spinors. Right, so eventually, you come down to 4 dimensions and you see how those 132 component spinor can lead to 8 different spin fields.
Yeah.
Right?
Remember that.
And they're particle-antiparticle pairs. I'm sure we've talked through that story. I assume it doesn't hurt to repeat a bit of this stuff. Right? Okay, so let's see what's next. This is important. The other thing I need to mention in this section, before we start
Chapter 3.
looking for the Dirac equation, I just want to make some remarks about the general properties of Lie algebras. And that'll probably...
The cows are around the corner.
Cows love this
They just eat grass. They're eating grass around.
They'll
eating grass.
Did I hear someone talking about Lie algebras? Oh, moo. All right. Okay. So, notice the form of this. This isn't actually as complicated as you might think. Basically, the product of 2 of these is an eta times an m, right? You could almost forget about all this. All the rest of this is just enforcing the anti-symmetry of these pairs of indices. It has to be anti-symmetric in RS. It has to be anti-symmetric in MN. So if you look at this first one, interchange RS, then add another term interchanging MN, then add another term where you interchange both, and you get these 4 terms. So you get a minus sign if you've interchanged one pair, you get a plus when you've interchanged both. So all of this just anti-symmetrizes those indices to match what has to be the case here. So it's not actually a hard thing to remember. If you remember that first term, you can write the whole thing. Now, when we do, since we have all done this, Maurer-Cartan equations for these, it's nice to have a factor here. So you define these with a factor. And I think the factor that works is -1/2 out here. So if you rescale your generators to get a -1/2, I think the Maurer-Cartan equations will work out the way we usually write them. But notice this is a nonlinear relationship. It's quadratic here and linear here. So you can actually get any constant here you want. There's no problem. It's just a simple rescaling of the generators. Okay, so I was getting the eraser. there are two essential properties of a Lie algebra. We're talking about we're talking about any Lie algebra here. So we find the infinitesimal generators of the Lie algebra, and we define a Lie algebra is a vector space okay, now a vector space, because we've linearized it, right? When we exponentiate an element of the Lie algebra, it's an arbitrary linear combination of the generators. We're in effect, we're exponentiating an entire vector space, right? All linear combinations of the generator, each one gives a different element of the Lie group. So the object we're really interested in, and the object we get from a Lie group, is first and foremost a vector space where the generators form a basis of vectors. Linear combinations then form the vectors. So the Lie algebra is a vector space, and it has a bilinear product anti-symmetric.
Bilinear makes me think of a metric a lot.
Yeah, but any rank 2 tensor, right? Any rank 2 tensor transforms bilinearly. So yes, the metric is a case. That's right.
It's not the metric isn't anti-symmetric though.
Satisfying one. Two properties. One, okay, so it closes with constants. What do they call these here? All right, any two elements of the Lie algebra, V and W. All right, what we're going to get is some, we're going to get some other element of the Lie algebra.
Can I put indices on it?
So for all U and V in the Lie algebra,
Big V.
There exists W such that this anti-symmetric product, V for the vector space, little v for an element, is going to be that W element of V. So an anti-symmetric linear product that closes back into V. And second, what's the second?
The
Jacob.
Jacob. Yeah. I'm like I can see it in my head.
Okay. So for all U V W in V, we have the commutator of U with the commutator of V and W. And can you tell me the importance of this? What does this guarantee?
Well, let's think.
The anti-symmetric part?
I don't know.
It's related to associativity.
Yeah.
Right? Now, as an exercise, I think I ask you to show, if these are just matrices, just write this out and it vanishes. Right?
Yeah.
So,
just like the thing for the Poisson brackets a while back, right?
yeah, that's right. That's right. Now, if you don't have a linear representation, if these are not matrices, that's not guaranteed. Associativity is not quite strong enough to that this is immediate. Right? No, I said that backwards. This is weaker than associativity. Okay, so certainly this is true if these are associative, but they don't have to be. They have to satisfy a relation like this. But what actually is the issue is that you can show that at first order, if you expand group elements infinitesimally, you can show at first or second, maybe you need to go to cubic order, that that this gives you associativity. But, and that's not too hard. The problem is knowing that at all orders, that identity continues. And that is really, really hard to show. But what's very, very easy to show is when you rewrite these two equations as the Maurer-Cartan equations, that's the integrability condition.
Okay, that's where I was
You were almost
thinking of
I can-
that.
Yeah.
Yeah,
And that's exactly what this is. This is the integrability condition for the Maurer-Cartan equations. The Maurer-Cartan equations,
Depends on-
we won't do this now, but you guys have seen this, so I'll write it. For each one-form dual to the generator, you get structure constants.
Yeah.
With omega b wedge omega c.
Yep.
And you would like this equation to be, this is completely equivalent to these commutators. And the integrability condition for this, which you get by the Poincare identity, if you just apply d to this and work with it a little bit, using the anti-symmetry of the
You
C's
get
and so
to the
on,
Jacobi identity.
you get to the Jacobi identity. Exactly.
Bum, bum, bum.
Yes. Zene. Okay, so the way to prove that this is required for Lie algebra is to show that it's the integrability condition for the product. Okay, now let's see. I'm wondering how much more of this I want to go through. We can use the structure of constants to produce a copy of the group. Have I talked about the adjoint representation?
No.
Yeah, let me just mention that, and that's probably enough here. So, suppose we write this in components. One thing to, one point to remember here. To get this product, linearity is enough. What we usually write are the commutators of the generators. But the commutator of U and V is just a sum over the generators, VB with some GB. And that's going to be, well, we know that that's got to be some W, which is W, let's call it CGC. But linearity means I can pull out these linear combinations, UA and VB, and just look at the commutator of these guys, the G's, the generators, and that's got to be some linear combination of the GCs. You can see where the structure constants have to come in, because this W has to be some sensible function of U and V, of the components of U and V. And in fact, what it is structure constant AB, or let's see, we're using capitals here, CAB, ABB. It has to be linear in them because this is just one other vector. It has to be linear because this has to work for every, because this is linear in U and V. Any term U, V, V, any higher powers of U and V won't be linear. So you have to be able to express this vector linearly with something that doesn't depend on which vector you're looking at. And so you get the structure constants here, and so this becomes equivalent to knowing the commutation relation for the generators. Once you have this, then you have the commutators for all vectors in the Lie algebra. Okay, then the adjoint representation. Suppose we have structure constants, CABC. These define the antisymmetric product. These have to be antisymmetric in those down indices. What we can do is we can define a matrix for the generators. What I want to do is let GA be a matrix so I want the CB components of that matrix to be CAB.
That better be
CAD, like this. All right, and I claim that that actually is a satisfactory choice for the generators. It's the way to see it is to look at the Jacobi identity. All right, now the Jacobi identity. Let's see. All right, if we write the Jacobi identity with the generators, the same that we just said for the commutation relations is true for this. It's true for all U, V, and W if it's true for the generators. B, G, C. All right, so let's write this out as a matrix thing. This is going to be G, A, and let's suppose, let's go E, F here. All right, so now this is going to be GA with the commutator of GB and GC.
Yeah.
But we can write that commutator as a structure constant DBC with GB.
Mm-hmm.
And now I can write that as
It's linear.
CDBC,
Yep.
and then this is going to be G. What do we need?
F something.
Let's see. We have AD here,
Yep.
and so we need what's like? Let's take a G, and then here we put a G. The EF components.
Mm-hmm.
Okay. Now.
And now you have two structure constants.
Yeah.
You could.
Yeah. I have to think how I want to do this. Yeah. Yeah. Okay. When I cycle these, it's going to give me this with A, B, and C cycle.
Mm-hmm.
So I'm going to get C, D, B, C, C, G, A, B, anti-symmetrized on ABC equals 0.
Mm-hmm.
So that's the Jacobi identity expressed in terms of the structure constants. But now, I can write this. Here we have C, D, B, C, C, G, A, D. Let's make that G into an E. It's too far down the alphabet. Okay, I was going to cycle ABC. C, D, C, A, C, E, B, D, and C, D, A, B, C, E, C, D, C. Right, that's got to be 0. That's the Jacobi identity written in terms of the structure constants. Mm-hmm. But now, I want to pair up these two. Mm-hmm. Right, this one, if I interchange here, I get a minus sign. So this one, I can write this as GA times GB. If I flip this and interchange those, I can write this as GB GA. It's the commutator. Right? It's the what's left. If I interchange these, it's going to be the EC component of the commutator. All right? Now, on the other side, What have we got? A structure constant. We leave that alone. And then this is another GC, the ED, not ED. Flip those. So it's GD, but we get a minus sign. I bring it to the other side of the equation. It becomes plus, and now we have the EB, EC. Yeah, that gives us the EC component of GD. But this is just the commutator. Now the indices match. This is GA, GB. Commutator equals C, D, A, B, GD. And we've got it. There we go. Okay, so this is called the adjoint representation, where we use the structure constants as a representation of the generators. And doing that, a lot of calculations are a little easier if you do that. You can prove a bunch of things. You would like your proofs to be independent of the representation, and sometimes they are, sometimes they aren't. But anyway, this is probably what we're going to need for the algebras. What I wanted to do next week then is to start talking about the Dirac equation and representations of the orthogonal and the Lorentz group. So if you know what to do with SU2, go ahead and prove that the action of SU2 on a vector is the same as the action of SO3 on that vector. What you have to know is how to write a vector, how to write a 3-vector, and how to transform it. Let me take just a minute to show you that.
Right. The cows are in fact outside.
The cows are outside the door. Okay. All right. Well, yeah, just quickly. I can write a vector as V dot the Pauli matrices. So what I'm going to get, well, sigma z is going to give me VZ here minus VZ there. Then sigma x gives me Vx, Vx. Sigma y minus I, Vy minus I, Vy. So there's this one-to-one mapping between a real 3-vector and a traceless Hermitian 2x2. All right, and what you want is the action of SU2 on this. A general element of SU2 can be written as e to the I phi over 2 n hat dot Pauli matrices, where I sigma are the generators of SU2. And if I sandwich V between a pair of those, one and its adjoint actually, the Pauli matrices are Hermitian, so it just changes the sign of I. Depending where you put the minus sign here, you're rotating one way or the other. So there might be, I might not be rotating the same direction we did. But if you expand this out using Pauli identities, this can be expanded in terms of the Pauli. So you're shuffling Pauli matrices, right? You can generate that same identity that we developed, that same rotation matrix that we developed for SO3. So have a go at that.